Okay, part 3 of the respiratory system. I have cleaned up my hard drive, so I should be able to continue on with this one and finish respiration with you tonight. The thing about the respiratory system is that it is controlled by receptors in the brain. It is voluntary, but it is automatic in the fact that the brain automatically signals it. And it's part of the brain called the medulla oblongata and the pons, which is part of the midbrain. But it is not oxygen that is the main regulator of the respiratory system. It is carbon dioxide. And the reason why is carbon dioxide easily goes across the blood-brain barrier. That's a little hard to say. So let's look at the different receptors. There are stretch receptors and there's chemoreceptors. So we talk about the main, there we go, the main variations. There are neural input and breathing despite neural input, breathing patterns do not remain constant. Respiratory rate and rhythm depend on pain, emotion, exercise, change in body's physical state. It occurs in the respiratory centers from a number of sensory receptors throughout the body, which aids in the body's changing needs. Now, when we look at the receptors, one receptor, the main one is carbon dioxide. A minor one, even though we talk about it first, a minor one is oxygen. If oxygen decreases, oxygen partial pressure or concentration, we look at it, and these are located in the carotid arteries and the aortic bodies, which are the main blood vessels. So the aortic bodies in the aorta, which just comes out of the heart and goes to the main body. And the carotid artery is the artery that goes to your brain. So low levels will cause these chemoreceptors to send an impulse to the medulla oblongata. Now think about logically. If you have low oxygen, you need to increase your respiratory rate in order to get more oxygen. So low oxygen will result in an increase in the rate and the depth. So you breathe faster and deeper, getting more air exchange into the lungs. So that is number one, chemoreceptors in your medulla oblongata that chemoreceptors in your carotid and aortic bodies, which signal the medulla oblongata to increase the breathing rate. Well, that's a lot of words today. Okay, the second one is pH. Now, we talked about how carbon dioxide can change the pH. Without going into too much detail, carbon dioxide will react with water. And it will create an acid called carbonic acid. Ooh, that's some pretty bad writing. Carbonic acid is H2CO3. Now, carbonic acid is not very stable, so it falls apart quite quickly, creating H+, which is the hydrogen ion, which is going to affect the pH, and your carbonate ion. Now, we'll talk about the carbonate ion quite a bit because that is really the main way that carbon dioxide is carried in the blood, because the carbonate ion is very soluble. So if you remember back to pH, if you increase the amount of pH or hydrogen ion, that will result in a decrease. If you increase the amount of hydrogen ions, that will result in a decrease in pH. Now notice that pH is little p, capital H. Okay? So that decrease in pH is detected by it monitors in the blood. It's detected by central receptors in the cerebrospinal fluid. So cerebrospinal fluid is the brain, the stuff that goes around the brain, and it's actually detected by the chemoreceptors in the midbrain too. Okay? Then the respiratory centers, basically if you have low pH, that means you have too much hydrogen carbonate. So what you do is you increase the depth and the rate of breathing, and you will blow off carbon dioxide. That will cause the reaction to go this way, and then carbon dioxide leaves the lungs, and as a result, you get your pH will then go back up to higher. Okay? So quite detailed in terms of the chemistry, but I just want you to realize that the amount of carbon dioxide will affect the pH. More carbon dioxide, more acidic. Okay? So that is how your carbon dioxide levels can be detected by your chemoreceptors in your medulla oblongata or your brainstem. Good. The third type of receptor, so you've got your oxygen receptors in your carotid arteries, you've got your pH carbon dioxide receptors in your medulla and your brainstem, and then the third type of receptor is in your lung walls, which makes perfect sense that you have a stretch receptor in an area that can stretch, and you don't want it to overstretch. So as the lungs inflate during inspiration, the receptors detect stretching and signal the respiratory centers in the brainstem, that's the pons and the medulla, to inhibit. So if there's too much stretching, it will prevent damage from inhalation by determining by the stretch receptors. The stretch receptors will then send a message to your brainstem, and that will decrease your rate and strength of breathing. Okay? Decrease your rate. Ooh, that's some bad writing. Good. The fourth one doesn't have a straight pattern. The fourth one is detected by pain and emotion, which can either stimulate it or suppress it. Sometimes if you're in pain, you will stop breathing. If you're sad, you will breathe faster. So anytime you see the limbic system is in charge of emotions. So your hypothalamus is your master gland, and your limbic system is in charge of emotion. Good. Now, this is a chart that everyone likes to quote, and it makes sense if you do any measurements. It is basically something you need to memorize. Your volumes are measured with something called a spirometer. And if you're doing normal breathing, in and out, in and out, in and out, your tidal volume, just as the tide goes in and out each day, your tidal volume goes in and out, and it's only half a liter. Then you can suck in air, and if you suck in air, this is your inspiration reserve, and it can be up to 3 liters. Then you can push out air, that is your expiration. And because of these alveoli little air pockets, you will always have some that does not move, and that's your residual value. Then the amount of air moving in and out each breath, or each strong breath or forced breath and forced exhale, is called your vital capacity, which is about 4.7 milliliters. And this will depend on your health, your age, and also the size of your person and your gender. Okay? So your total lung capacity involves your inspiration, your expiration, and your residual. So pretty much you need to know these definitions, and if I gave you this squiggly chart, you could define what each squiggle means. Good. The process of gas exchange, we talked about. Gas exchange has to do with pressure. And don't worry about these numbers, just realize that there needs to be a pressure difference in order for air to move. And it moves similar to concentration gradient, but it moves from high pressure or to low pressure. That's pretty much summarizing that one. Good. And that is, now transport. So we talked about the transportation of gases. When we talked about the red blood cell, we talked about the transportation of oxygen is attached to the hemoglobin. So realize that if pure oxygen was just entering the body, only a very small amount of the gas will be dissolved in blood. And that's because gases don't dissolve well in warm fluids. So 98% of it has a weak bond to the iron portion of hemoglobin, and it travels around on the hemoglobin. And then when it gets to the cells, this seems to be like a complicated graph, but it's not overly complicated. Basically, this says it has to do with the pressure of oxygen. If there is a large concentration of oxygen, it will saturate the hemoglobin, but it only saturates to a certain amount. Okay? So as soon as your first hemoglobin is filled, it will change the shape and it will move on, and then your second and your third. To me, it's kind of like the rides at Disneyland, that once one gets on, it'll move along and the next one will come. And this has to do with the dissociation curve. So the more oxygen you have, the more saturated your hemoglobin. Good. Now, carbon dioxide. Carbon dioxide travels 3 ways. The least way is dissolved in your plasma as bubbles. So the gas is dissolved. Again, warm fluids do not dissolve gas as well. The second way is bound to the hemoglobin. Now remember that it does not ride on with the heme and the iron. It's attracted to the outside of the globin molecule. And the third way, the most common way, is in terms of the bicarbonate ion. So when the carbon dioxide dissolves with the plasma, it reacts with the water, forming carbonic acid. Carbonic acid breaks down to carbonate ion and hydrogen. Okay? So that will explain those 3 different ways. Notice there are 3 ways, so that would be a good put in order, or good ways to distract you with bad answers. Good, and that is the end of the respiratory unit, because that was a lot of terms. Good, and so that ends it. Keep working hard. Make sure you go through and review it, because it seems like there's not a lot, but there's actually a lot.